Section 13 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy, Chapter 10, The Sun, 2, the Reversing Layer, the Chromosphere and Corona, Radiation Pressure and Solar Energy, Part 1. The so-called reversing layer was discovered by the late Professor Charles A. Young during the eclipse of December 22, 1870, on which occasion he placed the spectroscope with its slit tangential to the sun's limb so that it ran along a shallow bed of incandescent vapors. When the moon reduced the size of the crescent of the sun, the dark lines of the spectrum and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was covered by bright lines more numerous than one could count. This phenomenon lasted about 2 seconds and gave the impression of a distinct reversal of the Fraunhofer spectrum, showing bright lines for dark in every case. That such a reversing layer should exist was demanded by Kirchhoff's theory of the production of the Fraunhofer lines, and implied a stratum of mixed vapors at a lower temperature than that of the surface of the sun. It was by such a stratum that the missing rays of the solar spectrum were stopped. The spectrum from this portion alone could supply bright lines if the overpowering brilliancy of the solar background could be cut off, which can occur only at the time of an eclipse. This observation of Professor Young's, with its important bearing on the theory of Kirchhoff, was not confirmed until 1896, when photographic evidence was forthcoming. During the eclipses of 1898 and 1900, abundant corroborative material was obtained, and the reversing layer as a reality was conclusively demonstrated. The total depth of this reversing layer has been placed at from 500 to 600 miles. It continues in a normal state of tranquility, for little change is produced in the aspect of the dark lines. The chromosphere, or envelope of glowing gases, which covers the sun completely, was detected by observers of eclipses in the 18th and 19th centuries. There is a record in a letter from Captain Stannyan to Flamsteed, the British Astronomer Royal, describing an eclipse witnessed at Bern on May 1st, Old Style 1706, in which he states that the sun's, quote, getting out of the eclipse was preceded by a blood-red streak of light from its left limb, unquote. Halley and de Louisville in 1715 noted a similar phenomena, and it was also observed during annular eclipses of 1737 and 1748, but with the ruby brilliancy toned down to brown or dusky red by the surviving sunlight. During the eclipses of 1820, 1836, and 1838, similar observations were made, but it was not until the eclipse of the 8th of July, 1842, that the virtual discovery of the chromosphere as a solar appendage may be said to have been made. The eclipse of 1868, which was observed spectroscopically and photographically, as well as with the telescope, served to make clear the nature of the chromosphere and to reveal that it is a continuous envelope of hydrogen and other incandescent gases, some thousands of miles in thickness, and of the same eruptive nature as the prominences which are shot out from it. In other words, it seems to be a collection of minute flames set close together and giving it the appearance of a large conflagration. The summits of the flames of fire, which incline when the sun's activity is greatest, are erect during its phase of tranquility. The chromosphere is marked by an irregular distribution over the sun's surface, which in no way partakes of the character of an atmosphere. Professor Hale, in 1897, discovered a low stratum of carbon vapor. Such rare metals as gallium and scandium have been discovered with the spectroscope. The vapors of magnesium, iron, and several other substances are conspicuously represented in the spectrum of the chromosphere, and with the Yerkes telescope the fine bright lines due to the vapor of carbon also may be seen. The solar prominences are conspicuous eruptive or flame-like emanations from the chromosphere which are seen at total eclipses of the sun. They project like red flames beyond the dark edge of the moon, and were first described by Lector Vesenius, a Swedish professor of Gothenburg, who observed the total eclipse of May 2nd, Old Style, 1733. One of these reddish clouds outside of the solar disk was so large that it could be detected with the naked eye. The phenomenon excited his admiration and wonder. The prominences were also observed in 1778 by the Spanish admiral Don Antonio Ulloa, who was convinced of their connection with the Sun on account of their color and magnitude. By some observers, the solar prominences were regarded as the illuminated summits of lunar mountains, and by Arago they were described as solar clouds shining by reflected light. Abbé Peytal in 1842 spoke of them as self-luminous and as a third or outer solar envelope composed of the glowing substance of the bright rose tint which produced mountains, just as clouds were piled above the Earth's surface. In 1851, Hind, an English astronomer, noted on the south limb of the moon, quote, "a long range of rose-colored flames," unquote, which Dawes spoke of as a low ridge of red prominences resembling in outline the tops of a very irregular range of hills. Airy also noted this rugged line of projections and spoke of its brilliancy and nearly scarlet color. But the truly solar origin of the phenomena was not conclusively demonstrated until 1860, when the prominences were photographed by Secchi and De la Rue and shown to be independent of the motion of the moon. In 1868, with the growth of spectroscopy and solar chemistry, the gaseous nature of the prominences and their connection with the Sun was made evident. They were found to consist of immense masses of hydrogen and helium gas rising from the chromosphere and reaching an altitude of hundreds of thousands of miles. The corona. The corona is a beautiful lustrous solar wrapping which can be observed only during a total eclipse. The winged circle, the winged disk, or the ring with wings, as it is variously called, found upon Assyrian and Egyptian monuments, may be reproductions of the phenomenon. The first definite mention of a solar corona is to be found in Plutarch in connection with the eclipse which probably took place in 71 A.D. He writes that the obscuration caused by the moon, quote, "has no time to last and no extensiveness, but some light shows itself around the Sun's circumference, which does not allow the darkness to become deep and complete," unquote. Kepler mentions a ray of light seen around the eclipsed Sun in 1567 and ascribes it to some sort of luminous atmosphere around the Sun. In 1706, Cassini, observing an eclipse of the Sun in France, saw the, quote, "crown of pale light," unquote, around the lunar disk, and stated that it was caused by the illumination of the zodiacal light. Halley, observing an eclipse in London in 1715, describes minutely the phenomena of the luminous ring rising around the moon to a great height and showing considerable brilliancy. The eclipse of 1842 was the first to indicate the corona's great importance to astronomers, and from that date it received careful attention and earnest study. In 1869, Professor Harkness and Professor Young discovered a bright line of unknown origin in the coronal spectrum, showing that it consists in large part of glowing gases. With the advent of astronomical photography and with the development of the spectroscope, more attention than ever was given to the careful study of the corona in the limited time available on the occasion of a total eclipse. The corona is described by Professor Hale as a, quote, "faintly luminous veil of light extending outward in long streamers from the surface of the photosphere to distances of several millions of miles, and exceeded in brilliancy, even in its brightest parts, by the full moon. In many ways its streamers resemble those of the aurora borealis, and it is indeed possible that their origin may be ascribed to some similar electrical cause. During the few minutes of a total eclipse they are not seen to undergo change of form, but the outline of the corona does vary greatly from year to year in sympathy with the general variation of the solar activity. Spectroscopic observations have shown that the corona consists mainly of gases unknown to the chemist. That is to say, the lines in its spectrum do not coincide in position with the lines of any terrestrial element. Whether these gases, which are probably very light, will ultimately be found on the Earth cannot be predicted. Like helium, first known in the Sun, they may eventually be encountered in minute quantities in some mineral, where they have hitherto escaped the chemist's analysis. The fact that the lower part of the corona gives a continuous spectrum, with a feebler solar spectrum superposed upon it, indicates that minute incandescent particles are present, which are hot enough to radiate white light and which scatter enough sunlight to account for the presence of the solar spectrum." Unquote. The strange line in the green portion of the spectrum does not correspond with that of any element with which we are acquainted upon the Earth, and accordingly a hypothetical element has been assumed to which the name coronium has been applied. Chemical composition. Anaximenes' idea that the Sun was a glowing ball of incandescent iron came almost as near the truth as subsequent speculations by philosophers and astronomers, until about the middle of the 19th century. In 1859, Kirchhoff's great discovery of the explanation of the Fraunhofer lines in the solar spectrum made it possible to ascertain the chemical composition of the Sun. Thus, as has been shown, the bright colored band formed of light from a small hole in Newton's shutter passing through a prism made that prism the forerunner of an instrument able to teach the nature and constitution of bodies far distant in the heavens. Thomas Melville had examined with a prism various flames in which different substances had been introduced, and had reached the conclusion by the middle of the 18th century that certain vapors, notably sodium, contained light which had a definite place in the spectrum. Melville's deep yellow ray became the sodium line in the spectroscope of Fraunhofer. When Kirchhoff noted the identity of certain lines characteristic of terrestrial elements and then assumed their presence in the Sun, he laid the foundation of the modern science of solar chemistry. Wherever light can be observed from a heavenly body, it is now possible to resolve it into its spectral elements and thus to identify the substances. In fact, as substances such as helium were found in the Sun by Lockyer, which had no terrestrial counterpart, hypothetical elements were assumed. The spectroscope has shown in the Sun the presence not only of gases such as hydrogen and helium, but iron, sodium, magnesium, calcium, and many other substances. Hence, the chemical composition of the Earth and the Sun are much the same, although there is evidence of the existence in the Sun of substances not yet found in the Earth. When the spectroscope was applied to the analysis of the chromosphere and its prominences, it was found that they are composed of the vapor of calcium and of the light gases helium and hydrogen. Sunspots, too, have been found to have a characteristic chemical composition, while the corona emits rays which probably indicate the presence in it of very light and tenuous gases. With the light given off by the Sun, there is to be considered a phenomenon which only recently has been demonstrated by experiment, namely that light exerts a pressure which can act on minute particles quite as effectively as gravitation. Gravitation, however, attracts entire masses, but pressure acts only on surfaces, so that a force such as the pressure of light, to be effective, must deal with very minute masses. If you subdivide a mass into a large number of minute particles, the effect of gravitation is not changed, but a point will be reached in the subdivision where particles may be obtained having much surface and very little weight. If such a particle has a diameter of 1/100,000th of an inch, it will be exactly balanced in space, pulled by gravitation, weight on the one hand, pushed by light on the other. If the particle is even smaller than 1/100,000th of an inch in diameter, the pressure of light upon it pushes it away with terrific force. It is the radiation of the Sun acting on the minute particles that produces the phenomenon of comets' tails, and it is this pressure which may be responsible for the brilliant phenomena of the corona, visible only during the vanishing moments of a total eclipse. No one has ever satisfactorily explained how the highly attenuated matter composing both the prominences and the corona is supported without falling back into the Sun under the pull of solar gravitation. Now that Arrhenius has cosmically applied the effects of light pressure, a solution is presented. How difficult it is to account for such delicate streamers as the prominences on the Sun is better comprehended when we fully understand how relentlessly powerful is the grip of solar gravitation. The Sun admittedly projects vapors into space, vapors which must condense into drops when they encounter the cold of outer space. If the drops are larger than the critical size which determines whether light pressure or gravitation shall prevail, they will be snatched back by the Sun's gravitational attraction and give rise to the curved prominences that are often observed. If they have approximately the critical diameter, they will float above the Sun in the form of beautiful carmine clouds, balanced in space by the equal and oppositely acting forces of gravitation and radiation pressure. These clouds have hitherto been particularly puzzling, for in the absence of a dense solar atmosphere their existence seemed a celestial paradox. If the condensed drops are smaller than the critical diameter, they will be projected by the pressure of light far beyond the Sun to form the beautiful pearly corona. From the fact that comets have passed through the corona without any very apparent retardation, some idea of its tenuity can be gained. Assuming that the corona consists of particles of such size that the radiation pressure on each exactly equals its weight, Arrhenius finds that the entire corona weighs no more than 12,000,000 long tons, which is equivalent to 400 large transatlantic steamers, and is not more than the amount of coal burned on the Earth every week. Compared with the infinity of the space in which it is poised, the Earth is smaller than a vanishingly small speck on a sheet of paper having an area of many square miles. So far as the Earth is concerned, the Sun is very much in the position of a man who throws away all but a single cent of a fortune consisting of $23,000,000 for only 1/2,300,000,000th of his radiated energy reaches this globe. What then becomes of the huge number of corpuscles which are shot from the Sun and which never strike the Earth? It is conceived by Arrhenius and his followers that many of them must collide with corpuscles discharged by suns other than that of this solar system, suns ineffably distant, so that their light reaches the Earth only after the lapse of countless centuries, and so that they are seen not as they gleam now, but as they gleamed when Egypt was young and Greece was a wilderness inhabited by savages. Such collisions must result in the formation of large masses up to a limit determined by the electrical charges carried by the corpuscles. End of section 13.